In the late summer of 1977, two unmanned spacecraft, Voyager 1 and 2, lifted off from Cape Canaveral atop Titan Centaur rockets. Traveling uninterrupted through interstellar space, the Voyagers will endure forever, long after everything man has ever built has crumbled into dust. In the event the spacecraft encounter alien intelligence, both Voyagers carry a copper phonograph record, a message, celebrating the sights and sounds of Earth.
And friendly wishes.
These unique discs contain photographs of everyday life, as well as voices, offering greetings in 55 languages. There are also animal noises, the music of Beethoven and Chuck Berry, a baby crying, laughter, rain, and a heartbeat. All of the planets in Voyager's path were in perfect alignment, something that occurs only once every 176 years. The spacecraft were in position to visit all 4 of the outer planets, a grand slam, an interplanetary home run. In March of 1979, nearly 2 years after launch, the Voyagers approached Jupiter, the celestial body that so fascinated Earth's first modern astronomer, Galileo. Passing through the boundary where the supersonic solar wind slams into Jupiter's magnetic field, the spacecraft's instruments recorded a strong bow shock. Named after Jove, the supreme god of Roman mythology, Jupiter is an enormous whirling sphere of turbulent gases, big enough to hold over 1,300 Earths. The Voyagers discovered thin rings of dust encircling the planet, tiny grains containing silicon or carbon, like a fine haze of ash and smoke. Jupiter's atmosphere displays a dazzling variety of alternating patterns, cold, light-colored zones dominated by ammonia ice crystals in the higher altitudes, and warmer, dark belts of solid sulfurous particles in the lower altitudes. Voyager's cameras afforded scientists spectacular close-up views of the Great Red Spot, a storm 3 times the diameter of Earth raging in Jupiter's atmosphere. Voyager atmospheric scientist Dr. Andrew Ingersoll.
The Great Red Spot is a counterclockwise rotating storm, sort of like a hurricane, that has persisted for over 3 centuries. We were amazed that this spot could survive in the midst of all this turbulent activity.
With at least 16 known moons, Jupiter could well be considered a mini solar system. The Voyagers flew by the 4 largest, finding Callisto pockmarked by craters, Ganymede etched by icy parallel grooves, Europa smooth and icy, and Io glowing a cold and sulfurous red-orange. 9 active volcanoes were found on Io, the first observation of live volcanoes beyond Earth and Venus. These geysers were spewing hot, sulfurous gases 100 miles, high enough to hit a passing satellite. Voyager project scientist Dr. Edward Stone.
If I were to pick one discovery to represent the body of discoveries that Voyagers made, I would pick the discovery of the volcanoes on Io. These were totally unexpected and really forced us to reconsider our whole concept of the evolution of small moons which are orbiting in the outer solar system.
Pulling away from Jupiter after a joint reconnaissance of more than 6 months, the Voyagers got a healthy boost from Jupiter's orbit and made a beeline for Saturn. Mystifying man since the dawn of history, Saturn bears the name of the mythological god of the harvest, who reigned in the Golden Age. Traveling at more than 55,000 miles per hour, Voyager 1 arrived in November of 1980, only 12 miles off course after an interplanetary journey of more than 1 billion miles. Voyager's instruments found Saturn's atmosphere to be a cold ball of hydrogen and helium gases, racked by huge whirling storms and whipped by winds of up to 1,100 miles per hour. Saturn's magnificent rings, thought to have been the result of collisions between earlier moons and asteroids, consist of thousands of particles, swirling pieces of rock and ice, streaked like the grooves in a phonograph record. Voyager atmospheric scientist Dr. Andrew Ingersoll.
What Voyager discovered was the incredible structure in the rings. Saturn's rings are really composed of countless numbers of particles, ranging from the size of dust and perhaps larger particles the size of houses. These particles are constantly bumping into each other. These grooves are there because the rings are constantly being disturbed by satellites orbiting in with the smaller ring particles themselves.
As the Voyagers swept by, sunlight penetrated, backlighting and brilliantly illuminating the splendor of the rings, like the spokes of a gigantic Catherine wheel. Voyager 1 flew within 2,500 miles of the surface of Saturn's largest moon, Titan. One of only 3 moons in the solar system known to have an atmosphere, Titan may help unlock secrets to the origins of life. Voyager project scientist Dr. Edward Stone.
Certainly one of the more exciting discoveries at Saturn was the atmosphere of Titan. It's an atmosphere which is mainly nitrogen like that here on Earth, but which contains methane, so that the photochemistry going on there today may resemble very strongly that which occurred here on Earth billions of years ago before life evolved.
By swinging around Saturn, after a close-up view of Titan, Voyager 1 was propelled out of the plane of the solar system and is now traveling toward interstellar space.
In space, they say, no one can hear you scream. Nobody ever said anything about singing, though. A NASA spacecraft has just beamed back a beautiful song sung by our own planet. It's called Chorus, explains Craig Kletzing of the University of Iowa. This is one of the clearest examples we've ever heard. Chorus is an electromagnetic phenomenon caused by plasma waves in Earth's radiation belts. For years, ham radio operators on Earth have been listening to them from afar. Now, NASA's twin radiation belt storm probes are traveling through the region of space where Chorus actually comes from, and the recordings are out of this world. This is what the radiation belts would sound like to a human being if we had radio antennas for ears, says Kletzing, whose team at the University of Iowa built the Emphasis, electric and magnetic field instrument suite and integrated science receiver, used to pick up the signals. He's careful to point out that these are not acoustic waves of the kind that travel through the air of our planet. Chorus is made of radio waves that oscillate at acoustic frequencies between 0 and 10 kilohertz. The long antennas of the radiation belt storm probes are perfect for detecting these kinds of waves. Chorus emissions are front and center for the storm probe mission, says Kletzing. They are thought to be one of the most important waves for energizing the electrons that make up the outer radiation belt. In particular, Chorus might be responsible for so-called killer electrons, high-energy particles that can endanger both satellites and astronauts. Most electrons in the radiation belts are harmless, with too little energy to do damage to human or electronic systems. But sometimes these electrons catch a chorus wave, like a surfer riding a wave on Earth, and gain enough energy to become dangerous. The radiation belt storm probes are on a mission to find out for sure. The production of killer electrons is a matter of much debate, and chorus waves are only one possibility, notes Storm Probe's mission scientist Dave Cybeck. Launched in August 2012, the two probes are orbiting inside the radiation belts, sampling electromagnetic fields, counting the number of energetic particles, and listening to plasma waves of many frequencies. We hope to gather enough data to solve the mystery once and for all, says Cybeck. At the moment, the spacecraft are still undergoing their 60-day checkout phase before the main mission begins. So far, things are checking out very well. One of the things we noticed right away is how clear the chorus sounds in the recording, notes Kletzing. That's because our data is sampled at 16 bits, the same as a CD, which has not been done before in the radiation belts. This makes the data very high quality and shows that our instrument is very, very healthy. Eventually, Kletzing hopes to release unprecedented stereo recordings of Earth's chorus. We have 2 spacecraft with 2 receivers, he says, so a stereo recording is possible. Such a recording would not only sound wonderful, but also have real scientific value. One of the things we don't know is how broad the region is over which chorus occurs. The widely separated stereo capability of the storm probes will give us the ability to figure this out, he explains. With a 2-year mission planned for the storm probes, the Earth song is just getting started.
Deep within their roiling clouds, thunderstorms hold an elusive surprise. Under just the right conditions, they produce some of the highest energy radiation naturally found on Earth, terrestrial gamma ray flashes, or TGFs for short. Studies by NASA's Fermi Gamma Ray Space Telescope have shown that TGFs fire up about 1,100 times a day. Now, new research combines Fermi detections with ground-based radar and lightning location data. These studies show that TGFs come from more diverse types of storms than previously thought. In a thunderstorm, collisions among rain and snow cause different parts of the cloud to develop positive and negative electrical charges. When the strength of the electric field overcomes the insulating properties of air in the thundercloud, a lightning flash occurs. Most lightning occurs entirely within the cloud and is called an intra-cloud flash. All lightning produces a strong and sudden change in the storm's electric field, but the upward portion of an intra-cloud flash sometimes sends a surge of electrons rushing toward the upper part of the storm. Reaching speeds nearly as fast as light, these accelerated electrons give off gamma rays when their paths are deflected by air molecules. Using global lightning location networks, scientists can determine the TGF position more accurately than with Fermi data alone. 24 localized TGFs occurred within areas covered by next-generation weather radar systems. This gives scientists the opportunity to begin studying the kinds of storms that produce TGFs. These slices of radar data capture different types of storms encompassing a wide range of updraft strengths. Even the weakest of them produced a TGF. Another finding, TGFs seem to occur in the same altitude range, between 7 and 9 miles high. Lightning can form at much lower altitudes, so there's every reason to think TGFs can too. But gamma rays from TGFs occurring deeper in the atmosphere are greatly weakened. They're too dim for Fermi to detect, which probably means the satellite is undercounting them. TGFs may be far more common than we think. With this knowledge, scientists can design experiments to track storms and study how TGFs relate to their strength and evolution. This will give us an even better understanding of planet Earth's most powerful natural particle accelerator.
All of these spectacular happenings are visible manifestations of its existence. An electrical circuit that links the top of Earth's atmosphere, where charged particles are plentiful, to the Earth hundreds of miles below. Scientists at the University of Colorado, Penn State, and the National Center for Atmospheric Research are working to develop a scientific model of the processes across various spatial and time scales within the global circuit.
So one of the important aspects of this project is that there have been measurements taken about the electrical system for the last, 90 years, since 1930, for nearly a century. But there are no really good established models that allow one to verify the interpretation of those measurements and the physical pathways that lead to those measurements. Some of them have profound implications, but we need models to establish their credibility.
Sprites, elves, and blue jets, all shown on this mural, are collectively called transient luminous events, or TLEs, and are believed to be part of the global electric circuit. Red sprites, first verified in 1989, occur from cloud tops up to 95 kilometers, or approximately 10 to 60 miles, in the atmosphere directly above lightning strike activity occurring below. They last no more than a few milliseconds and can resemble carrot tops, columns, or jellyfish in shape. Elves are large, expanding, donut-shaped luminous events, up to 190 miles or 300 kilometers across, that occur for only 1,000th of a second. They too occur over lightning activity, but are believed to result when an energetic electromagnetic pulse propagates from lightning into an area of the atmosphere called the ionosphere. It's brimming with electrically charged particles and at times auroras. It extends from about 35 to more than 1,000 miles in the upper atmosphere. Lastly, blue jets emerge from the top of thunderclouds, then fan out and disappear after about 1/10 of a second, at heights of approximately 40 to 50 kilometers or 20 to 30 miles. They are the only transient luminous event not directly associated with cloud-to-ground lightning. They were first documented in 1994. We have a lot more to learn about transient luminous events and their role in the global electric circuit. For that matter, we have a lot more to learn about the circuit's many contributors, from clouds to atmospheric particles and more. Scientists working at the frontiers of this science are leading the way.
We think that by pursuing an improved knowledge of the whole global electric system, that discoveries will emerge that we might not have even have anticipated. And that's the way basic research goes. It wouldn't be called basic research if we already knew what the outcome was going to be.
What is the cumulative effect of Earth's thunderstorms that charge the planet's electric circuit up through the ionosphere? What processes contribute to earthward current on clear weather days? What unknown roles might electricity play in our weather, our climate, and throughout our amazing, electrified atmosphere?
May 10th, 1996, hour 16, minute 38, AKR.
The University of Iowa's Polar Plasma Wave Instrument. Wideband receiver audio data.
At any given moment, about 1,800 thunderstorms are in progress somewhere on the globe. New observations by NASA's Fermi Gamma Ray Space Telescope show that thunderstorms make antimatter. The process starts with a terrestrial gamma ray flash, or TGF, an intense pulse of gamma rays originating from thunderstorms. These dots mark TGFs observed by Fermi's Gamma Ray Burst Monitor during the spacecraft's first 8 months of operations. Researchers estimate that there may be as many as 500 TGFs each day. On December 14, 2009, as Fermi passed over Egypt, it spotted a TGF produced by a thunderstorm in Zambia. The TGF was over the spacecraft's horizon, where Fermi couldn't see it. So how could Fermi have detected it? Scientists believe that the TGF process begins in a thunderstorm's intense electrical field. Electrons within this field become accelerated upward. Above the storm, where the air is thin, the electrons can ramp up to speeds nearly as fast as the speed of light. When these ultra-fast electrons encounter an atom, they emit gamma rays. Very rarely, one of these gamma ray photons grazes an atom and transforms into a pair of particles. One, an electron, is normal matter. The other is antimatter, the electron's opposite, called a positron. The gamma rays travel in straight lines, but the charged particles spiral along lines of Earth's magnetic field. And that was the route to Fermi. The particles created by the TGF rode upward on magnetic field lines and then struck the spacecraft. The positrons annihilated when they struck electrons in Fermi, creating a flash of gamma rays. For an instant, Fermi became a gamma ray source and set off its own detectors. A fraction of a second later, some of the particles were bounced back along the same magnetic field line. They again passed through Fermi and again produced gamma rays. The spacecraft has observed this phenomenon on at least 4 other occasions. So the next time lightning flashes and thunder roars, remember, you may be witnessing antimatter in the making.
gravitational waves are curves in the shape of space-time that propagate and carry energy. One way to think about space-time is the curves that things fall along around an object. So I could in some sense paint the shape of space-time by dropping things around the Earth and watching them fall. Now if the Earth were to move around and collide with the sun, those curves have to change with them, and it creates like a wave in water. And those are the gravitational waves. So let's say you have two black holes colliding. They're like mallets on a drum. The shape of the drum begins to rumble in response to the motion of those mallets, and it creates effectively like a sound. If you would record the shape of a ringing drum, you would play that back as sound. And that ringing of the shape of space-time travels through the universe at the speed of light, basically unimpeded until it washes over the Earth. And so when it's played back to us, it will be played back as different sounds. So let's say two black holes collide. It has a very characteristic, what we call a chirp. It gets louder and higher in frequency as the black holes collide, and you literally hear this sort of chirping up sound. And so the big ambition with these experiments is to record the shape of space-time ringing and to reconstruct the motion of the mallets and the shape of the mallets and what was going on when the sound was emitted, however long ago, a billion years ago, or however long ago.